right, welcome back everybody for another episode of Business Calculus. We're on section 1.3 and the title of this section is Average Rate of Change and Relative Change. Average rate of change, very important to us, very important. Relative change, not that important to us, not that important. All right, so we're going to focus more on average rate of change in this section. So let's get started. So let's recall something that we talked about previously. We introduced the idea of a positive and a negative graph, or a positive and negative function. And this refers to the quality of a function being having positive y values, meaning it lies above the x-axis, or negative y values, meaning the function lies, or the graph lies below the x-axis. Or perhaps you could have a 0, it could cross through the x-axis. Alright, so we talked about how this is like the first kind of level that you need to understand when talking about functions. Alright, so we talked about this before. We also talked about what it means for a function to increase or decrease. So let's remind ourselves of what that means. So a function is increasing if it's going up from left to right, if the graph is going up from left to right. Or if you have a table of values, those y values must be getting bigger, meaning that they need to become less negative or more positive. Right? They need to be going, if you have a real number line, they need to be going this way. Real number line for a decreasing function needs to be, those numbers need to be going towards the negative. Okay. So this function is increasing on this bit because it's going up from left to right, decreasing, and then increasing. Right? So it switches from increasing to decreasing these points, this maximum here and this minimum here. All right. So this is the next level that you need to understand things. And this might be a good time to also mention, if I were to find the average rate of change or the slope between 2 points where it's increasing, what could I say about that average rate of change that I should get? What would I expect to get? What kind of number would I expect to get? If I took the average rate of change on any 2 points over here, I should get a slope that's a positive number. Okay? There is a subtle interplay going on in all the terms that we're going to discuss between the concept of positive and negative and increasing and decreasing that you'll need to understand very well, or at least I hope you will. So the function is increasing. That means the slope is positive. The slope is positive. It's sloping upwards. And then while it's decreasing, it's sloping negative. It's sloping negative. Even though the function is positive, the function is always positive. It's always above the x-axis. But the slope becomes negative. Okay? And then the slope becomes positive again when it's increasing. So keep that in mind. Try to digest that. And let's move on. We talked about this last time on how to use the slope formula between 2 points. We use the formula y2 minus y1 over x2 minus x1. And we talked about how the units for a slope will always be a fraction. It will always be the units of y over 1 unit of x. That's how to get the units for a slope. And you'll have a lot of practice coming up with that. So that should become clear soon. And in the last slide, I mentioned how increasing functions have a positive slope, whereas decreasing functions have a negative slope. So it's a little bit difficult to get straight everything here. So don't make the mistake of saying it's an increasing function, so it's a positive function. No. Increasing function, positive slope of the function. All right. So whether the function is increasing or decreasing, it doesn't really tell us anything about whether the function is positive or negative. It only tells us whether the slope is positive or negative. All right. So just as an example, if I took the same function and I just shifted everything down, I just brought it all down, well, then it would be a negative function, but it would still be increasing on the same bits. Okay, so that's that. This is the third this is the third level of subtlety that I'd like to talk with you about. It's called concavity. Now, why are we talking about a term called concavity? We're not talking about whether prisoners have access to dental care or not. No. We're talking about what's happening to the slope of the function as we move from left to right. Okay? So, what does it mean for a function to be concave up? It means that the slope is increasing. Alright, I'm going to give you a second for that to digest, because hopefully you're realizing that's not the same thing that we were talking about before. The slope increasing, before we were talking about an increasing function, which meant that the slope was positive. The slope being positive is different from the slope increasing. It's that subtle difference between a function being positive, or a slope being positive, and a function or slope increasing that you're practicing making the distinction of. Alright, and a function is concave down if its slope is decreasing. Alright, so a helpful way to recognize whether a function is concave up or not is the phrase up like a cup and down like a frown. If it's up like a cup shape, it's concave up. If it's down like a frown, it's concave down. Alright, that's a way to immediately look at a graph and be able to tell whether it's concave up or concave down that you should use. However, you should also understand what it actually means for it to be concave up. It means that its slope is increasing. So for example, look at how it's sloping as we move from left to right. It's sloping downward at first, but notice that it's going down by less and less. And then it starts going up by more and more. So this slope is always going up. It's a negative number. The slope is negative, but then the slope becomes less negative and more positive. So the slope is always getting bigger. Alright? And over here we have the opposite case. We have a slope decreasing situation where it's sloping upwards at first. It's kind of very steep, but then it becomes less steep. So the slope goes from a positive number to like a less positive number on average. And then at some point the slope becomes negative and then more negative. So we might say that it's increasing by less and less and then decreasing by more and more. If it's either of those cases, then it's concave down. Alright? It doesn't have to have this full shape to be concave up. Maybe it just has this shape right here, and then maybe this right bit looks different. Then we would say over here it's concave up, over here we don't know. We don't know. So let's look at an example. Here's the graph of y equals minus x cubed. Now this function changes. Oh, there's a typo. It should say it changes. Well, you tell me what the typo is. That's your quiz. I did this on purpose so that you would have a chance to notice my error. Well, I didn't actually make an error. I don't make errors. But, okay. What it should say here is it changed from concave up to concave down at x equals 0. This is concave up. It's part of a cup. This is concave down. It's part of a frown. And this point where it changes, concavity, is called an inflection point. It's called an inflection point, x equals 0. Okay, so that's that. Let's see, notice the function goes, this part is actually correct. So let's practice here. Let's practice, because we got 3 levels of understanding for functions that we're talking about here. We're talking about whether a function is positive or negative. It's positive over here, it's negative over here, because we're just looking at where the function is in reference to the y to the x-axis. And then whether a function is increasing or decreasing, that's like the next level. It's decreasing over here. How about over here? Also decreasing. Also decreasing. It's always decreasing, actually. And then now we have the concept of concavity, and we would say that it changes from concave up to concave down. Okay, so these 3 concepts can all be mixed and matched. There can be a function that's positive but decreasing but concave up, and you could switch any of those. So if you're trying to get this stuff straight, you might try to draw out a function that is decreasing, negative, and concave up, or something like that. Try to mix and match. I guess there's 8 possibilities. 2 for 3 concepts. Okay, so let's move on. And we need to talk about distance, time, and velocity here. We actually already started talking about this relationship in the last video, I think it was. And but we'll just do it some more. So it's very common to write s of t to represent the distance that an object travels in t seconds or minutes or years or whatever. So you'll see that a lot. The distance function, let's say like a car driving or whatever. S could represent the distance. Why don't they use lowercase d? Well, we use lowercase d for other things, so blah, blah, blah. Anyways, the slope of the distance function is average velocity. All right, the slope between 2 points of the distance function is average velocity. So if I use the slope formula, I can find out on average how fast the object was moving. Let's see an example. So suppose I throw a ball up in the air. The height, s, which is measured in feet, is given at time t seconds after I throw the ball. Alright, so I'm throwing up a ball in the air, and I have a table here. I don't have a graph or a formula. I have a table. It starts at 0 seconds. Initially, it starts at 6 feet. I'm holding the ball way above my head, apparently. And then it goes up to 11 feet, and then up to 15, and then back down to 11, and back down to 6. So what's happening here? Gravity is taking into pulling the ball back downwards after I threw it up in the air. Okay. Find the average velocity from t equals 0 to t equals 2. We will use the formula that we just learned, which is the slope formula in this case. And we'll just find the y value at t equals 2, which is 15. The y value at t equals 0, which is 6. And I will divide by x2 minus x1, which is 2 in this case. So we have 9 over 2, which is 4.5. How did I know the units was feet per second? Well, what's the top measured in? It's the height. It's measured in feet. What's the bottom measured in? It's measured in seconds. That's why it's feet per 1 second. So each second, it increased by 4.5 seconds. On average, over this interval. All right. Notice that we got a positive number when we computed the slope. A positive slope means the function is increasing. All right. Positive slope means the function is increasing. It's increasing on this interval, isn't it? The y values are going up. 6, 11, 15, those numbers are getting bigger. Right? We're not talking about whether the function is positive. It doesn't matter that these numbers are positive. It just matters how they're changing, and they're going up. They're going up. All right. So that's that example. And we have one more thing that we need to talk about that's not going to be super critical to us, but it actually will be helpful to set the stage for exponential functions, which we're going to talk about soon. And that is the concept of relative change. So far we've talked a little bit about change, rate of change, which is the amount the y value is going up per increase in x value by 1. But we may not just want to know how much the y value is changing. We may want to know where it started as well, so we can get an idea of it may help us put that change in context. So for example, well, let's do this example and then I'll tell you another example. So let's say let's just practice using the formula first. So let's say we have 5 apples and then one more magically appeared in our basket of apples, and so we had 6. Let's compute the relative change. So the formula says to put the change, how much did it change? Well, we had 5 and we went to 6, so that increased by positive 1. So we have a positive 1 change. And then the initial amount, that's the amount that we started with 5. We started with 5, and 1/5, that's 0.20. And when I move the decimal 2 places, I can express that as a percent. That's 20%. And it's a positive 20% because it's an increase. Okay, so we increased the number of apples that we had by 20%. On the other hand, if we had 5 and then 1 disappeared from our basket, then we had 4, what would that relative change be? Well, the only difference now is that the change would be negative because we have 1 less. And negative 1/5, that's negative 0.20, which when I move the decimal, that's a negative 20%. So this would be a decrease of 20%. When we say decrease, we don't need to say the negative. We just say a decrease of 20%. Decrease takes into account this negative sign. All right, this is helpful sometimes because let's say we were talking about a number that was like starting with 1,000. Or let's say that we increased by 10 and we were starting with 1,000. All right, well, is that a very significant increase from 1,000 to 1,010? Not really, right? Depending on what we're talking about, of course, but just looking at the number, I mean, just not knowing anything else, it doesn't seem very significant. On the other hand, if we started with 10 and we increased by 10 to 20, we increased the same amount, but now in this situation, we've doubled. So in my mind, that's probably more significant, right? So that's why the concept of relative change is helpful. And it comes into play for exponential functions, which change by a constant percent. So they have a constant relative change, which is their characterization, instead of having a constant average rate of change. But we will talk about that more next time. Have a good day, and good luck on your WebAssign. No, you don't do WebAssign. Wiley Plus. Sorry, I might say WebAssign for that. Anyways, goodbye.